We're going to be taking a look at numbers 5 and 6 from the projectiles launched at Angle's review paper. In number 5, you throw a ball toward a wall with a speed of 25 meters per second. There's the hypotenuse of the triangle that I've drawn for velocity. And it's at an angle of 40 degrees above the horizontal. So there's the 40 in the bottom left corner of this triangle. The wall is 22 meters from the release point of the ball. So that would be our displacement in the x direction, 22. You can see we wrote that over here. How far above the release point does the ball hit the wall? So we're looking for displacement here in the y direction for where it would get to the wall. And what are the horizontal and vertical components of the ball's velocity when it strikes the wall? And finally, we want to know, has the wall passed the highest point in their trajectory when it hits the wall? We'll be able to answer that once we find the velocity components here when it gets to the wall itself. First thing, like with all of these angled projectile problems, we need to find the velocity in the x direction and the velocity in the y direction when our problem starts. Velocity in the x is the adjacent side. So we're going to use the cosine of the angle, 40 degrees, times the hypotenuse, which is 25 meters per second, to get the velocity in the x direction while this thing is in midair is 19.2 meters per second. The y direction is the opposite side of this triangle, so we're going to use the sine of 40 times the hypotenuse of 25, getting us the initial velocity in the y direction as an upward 16.1 meters. So you can see we put our initial velocity in the y, 16.1 here, and our 19.2 meters per second there in our x column. All right, now we're trying to find this maximum height, and that would mean d is our question mark, and you might wonder, when it comes to the final velocity and the d, how come we're able to do this all in one particular setup, whereas in some of the previous problems, we've had to do two different setups for maximum height and also finding maybe how far it went in the range position. The reason why we can do this all in one go is we're looking for the height at the point where it hits the wall, and we're also looking for the velocity when it hits the wall. So this is still here with our x and y columns, setting up a trip from when it got thrown to when it hits the wall, which is one trip. We're not worried about two different ending points like we were in some of the previous problems. So we can set this all up in one sort of problem, one set of initial conditions, and we can solve from there. In order to solve for the height, we're going to need more information because we only have v naught and a. So we can solve for time in the x direction because we have enough information there, and then use it in our y direction. So in the x direction, displacement equals velocity multiplied by time, because this is constant velocity motion in the x direction for all projectiles. Rearranging, we're going to divide vx over to the left, giving us time equals displacement divided by velocity. Our displacement in the x direction is 22 meters, and our velocity in the x direction is 19.2 meters per second. Divide those two numbers, and we get a time of 1.1 seconds. From there, we can figure out how high the ball is going to go in 1.1 seconds using our y column information. We're going to use the equation without VF in it because I don't have VF, so we're going to use the third equation, d equals v naught t plus 1/2 at squared. V naught is 16.1 meters per second. Time, we solved for 1.1 seconds. Acceleration, negative 9.8. And time is again 1.1 seconds. This is squared, although it looks like it faded a little bit when it got photocopied and scanned, but that squared should be there. Make sure that you have it for yourself. And we plug all that into the calculator, we get a maximum height of 11.8 meters. Now, figuring out what the velocity components are when it gets to the wall right here. Well, the x component's very easy to solve for because we don't have to do anything. It's always the same. It's going to be 19.2 meters per second in the x direction, the entire path of all projectiles that are in midair. The x never ever changes. So now we just need to find the final velocity in the y direction. I'm going to use the equation that doesn't have the displacement in it because we already solved for that one. So we'll not use it to solve for something else, just on the off chance that we got it wrong. We didn't. But just in case you would have, maybe you would want to use the equation that doesn't have the displacement in it. And that's the first one, VF equals V naught plus AT. But if you wanted to use one of the equations that have D in it, that's perfectly fine as well. This one's already set up for VF, making my life pretty easy. I just have to plug in my numbers. The initial velocity in the y direction is 16.1 meters per second. A is negative 9.8, and time is 1.1 seconds. Plug all that in my calculator, and I get a positive 5.3 meters per second. Because the final velocity when it gets to the wall is positive, meaning upward, that means that the ball is still traveling upward. It has not reached the highest point yet on its trajectory. So it is still on the way up and still moving upward again because the velocity is positive. So that answers the last part of the question. Moving on to number 6. Number 6 is a tricky one. Not that the physics is all that tricky, but the math can be a little bit of a bear. So hopefully you can follow along with me. In number 6, a pitched ball is hit by a batter at an angle of 45 degrees. So there's my bottom left angle to this particular triangle, and just clears the outfield fence 98 meters away. So my displacement in the X direction from where it's hit to the outfield wall is 98 meters. You can see that's put here in the X. Assuming that the fence is at the same height as the pitch, that means that the ball starts at a particular height and ends at a particular height. So our displacement in the Y direction is 0. Find the velocity of the ball when it leaves the bat. So you might notice, well, without the hypotenuse, which is the actual velocity the ball has when it leaves the bat, we can't solve for the velocity in the X or the velocity in the Y. But we can set up what we know for the velocity in the X, that's the adjacent side. So if I were to solve it, it would be the cosine of my angle, 45, multiplied by the hypotenuse. The velocity was what we're trying to solve for here, v. In the Y direction, I can do the exact same thing, but it's the opposite side on this triangle. So I'm going to use sine of 45 times v. I know the acceleration is negative 9.8 meters per second squared. And now I'm out of information. So we only have one equation in the X direction, which is d equals v times t. And in the Y direction, I'm going to pick the equation that does not have Vf in it, because Vf has no relation to what's going on in the X direction. But I do know they have time in common. So I'm going to use time and not Vf when I pick an equation. So I did the third equation, d equals v naught t plus 1/2 at squared. And you might notice that we actually have a simultaneous equation. We have d, and in the velocity in the X, what we don't have is the velocity part. We know the angle, we don't have v. So v and time are two things we don't have in this particular equation. And then in the Y direction, I have d is 0. V naught, I don't have the v. So again, my unknown is v, and I don't have time. And then we have a, but I don't have time. So what we are missing in these two equations is the velocity and the time. I have two equations and two variables. So this is a simultaneous equation. It's just a little bit of a tricky one. And I'll show you how this works out. So if I rearrange my X equation for time, I get displacement in the X, 98, over the velocity in the X, which is cosine 45 times v. I'm going to take this dx over v, and I'm going to plug it in everywhere in the Y equation where I have time. So you can see I wrote that here. Substitute the displacement in the X over velocity in the X for time. And you can see what that looks like right here. So d in the Y direction equals the initial velocity in the Y over displacement in the X and velocity in the X in the denominator, plus 1/2 a, and instead of t squared, I have dx squared over vx squared. Now what we can do is, instead of having our v in the X and v naught, we're actually going to plug in our cosine 45v and our sine of 45v. And I plugged in my d is equals 0 and all the rest of my numbers because it might make my life a little bit easier. So d in the Y direction is 0 equals sine of 45v, because that's what v naught is, sine of 45v, times the displacement in the X direction. You can see that's here, so that's 98, all divided by the velocity in the X direction, which is cosine 45v. So that's in the denominator. Plus 1/2 acceleration is negative 9.8 meters per second squared, times d in the X, which is 98 squared, divided by v in the X, which is cosine of 45. That has to get squared, and v, which also gets squared. They both get squared when you would have a square for this vx here. This is going to simplify a little bit. Sine of 45 over cosine of 45 is tangent of 45, which is just 1. And v divided by v cancels out, also being just 1. So what that leaves me with here, since sine 45v over cosine 45v equals 1, 1 times 98 is just 98. So this whole big ugly term just simplifies to be 98. Over here, I can actually plug in all my numbers in the numerator, 1/2 times negative 9.8 times 98 squared, and that gives me negative 47,059.6. The units would be meters cubed per second squared. And then in the denominator, I didn't do anything. I left that as cosine squared 45 times v squared. So you can see that right here is unchanged. Now what I want to do is I'm going to subtract this 98 over to the left side. So that way I get my fraction all by itself here. So I did that, and I have negative 98 now on the left equals my fraction of negative 47,059.6 divided by cosine squared 45 times v squared. From here, I'm going to get this cosine squared 45 v squared out of my denominator by multiplying this whole denominator up to the left. So that gives me negative 98 times cosine squared 45 v squared. That's going to equal my 47,059.6. And then from here, I can just divide out the negative 98 and the cosine squared 45, divide that whole thing over into my denominator. So you can see that's hanging out down here. Negative 98 cosine squared 45. And in order to get rid of the squared with the v squared, I did the square root. Plug all that into my calculator, and all that ugly math, which might be a little bit confusing, comes out to a nice easy answer of 31 meters per second.